Hey guys, welcome to day 3 notes. So for the day 3 notes, you'll notice that it's on linear relations. So we'll be talking about graphing, scatter plots, making relationships or distinguishing relationships between the variables, and also taking a look at a table of values. Okay, so all the notes are on D2L. As usual, you will do the first evaluation on day 2 material. Okay, so that's an online quiz that you need to complete. Okay, so please do that first. The second thing you will do is go through the modules. The modules are already preloaded for you, and they cover topics like these. So 3.1, 3.2, 3.3, all the way up to 3.9. As a note, 3.7 is a quiz, so that's an activity that you have to do on your own. The 3 represents here that I've just highlighted the day 3 notes or the unit 3, and the number that comes after represents its activity number. Okay, so please go ahead and for your second step, ensure that you complete those modules. What is here in the PDF are just support notes. Okay, so with support notes, again, if you want to print them, you can, but they're meant to just enhance your learning in case you needed to clarify anything, you had a set of notes similar to a textbook or having unit notes in your own binder that help you with the lessons and support the modules that you should be going through. Okay, so I just have some keynotes here. In total, there are 14 pages, and I will go over them. There are also some homework support questions in this PDF document that you can also go through. They are not going to be collected, but they are meant for you to help support your learning once again. Okay, so the things that will be due for today will be that Unit 2 quiz you need to do. There's going to be 4 activities for the modules today, so a 3.4, 3.7, 3.9, and 3.10. Okay, so we'll get started here. I have mentioned here for 3.1 and 3.9 just to refer to the D2L module, as I find that it explains it quite well, and you could just look on to the modules for that. And for the ones in between 3.2 to 3.8, I'll show you some support documents, which is what I'm going to do in this video right now. Okay, so I have here the definition of a relation. So a relation is a description of how two quantities are connected. The two quantities that change together are called variables. So some examples of variables can be time, can be length, can be area, can be number of popcorn bags sold, could be number of hours worked. You might recall some of those examples from your school year. One quantity will depend on the other and is called the dependent variable. The other is called the independent variable and is the variable whose values you choose. Okay, now in terms of just differentiating the independent versus dependent, X is the independent variable. So some examples of an independent variable would be time, hours worked, number of popcorn packages sold, number of tennis balls sold. Some examples of the y coordinate, which is your dependent variable, could be costs, could be amount paid, could be area, could be the amount of distance traveled in that time that was allotted. So whatever it is, it basically depended on the independent variable. Okay, so the independent variable can exist on its own. The dependent variable depends on another variable to create its value or its representation. Okay, so hopefully that makes sense, and I'm sure you guys in your own individual classes earlier in semester 1 have gone through different examples. I just named a couple of them for you to refer to. Okay, so we're going to look at this next portion. So it reads, the data applicable in a relation can be either discrete or continuous. Discrete data cannot be broken into smaller parts, so the points on the graph are connected with a dotted line. Continuous data can be broken down into smaller and smaller parts and still have meaning, so the points on the graph are connected with a solid line. Okay, so that's just some helpful information for you for when you do some graphing. Okay, if you do not have graph paper at home, remember you can always use Desmos. Okay, so I'll just write this out here. Desmos is a website, desmos.com. It's also an app you can download into a device. And basically it is a graphing software where you can actually type in an equation, you can type in coordinates, and it will graph for you. All right, so let's take a look at this example here. So we have a plumber charges a flat fee of $50 plus $35 per hour for a service call. Okay, so what is the independent variable? So in this case, the independent variable is time. Okay, so meaning how many hours is actually spent for that service call. Okay, your dependent variable is the total charge. So how much it actually cost in dollars for the plumber to actually work on the work that's needed in your home. We can make an equation here. So you might recall let statements from earlier on. So we're always going to include let statements when we use variables so that we know and understand what these variables represent. So we're going to say let T represent the time worked in hours, and we're going to let C represent the total charge in dollars. Okay, so our equation, I'll just do it up here. Our total costs, so this plumber charges $35 for every hour plus a $50 flat fee charge. Now, flat fee means that is your fixed cost and it is only paid one time. Okay, so even if you get 8 hours of this plumber's work, you don't have to pay $50 each time. It's just that one initial charge of $50 at the very beginning. Okay, we're going to learn how to apply this in a table of values. Okay, so we're going to complete a table for up to 8 hours. So I'm actually just going to skip some values here just to make it easier. So we're going to see what happens at 0 hours, 2 hours, 4 hours, 6, and 8 hours. Okay, so the math that we'll be using in this example is using our formula. Okay, so 35H plus 50, and we're going to find out what C is. Okay, so let's pretend I meet with the plumber and I spend 0 hours. So I'm going to sub in 0 for H. Now I still need to pay for the $50 of that flat fee. Okay, because that's his charge. He still came over to sit down and, or he or she still came over to sit down and assess the situation. Okay, now we're going to see what happens if that plumber spends 2 hours. Okay, so in your calculator you can calculate 35 multiplied by 2, okay, and then add the $50 charge. You should get 120. We'll see what happens at 4 hours. Same thing, you should get 190. Okay, and then I'm just going to write out the values down here because I think you get the gist of it. We're just subbing in these values of H in for H in the equation. Okay. All right, so now in terms of graphing, okay, we'd have to make sure that we label our axes. Okay, so this is going to be our independent axes. So time in hours. Okay, so because I have a lot of space, I'm actually going to go every 2 boxes represents 1 hour. 3, 4, 5, 6, 7, 8. Okay, so when you're labeling this, remember you have to choose your increments, and you got to choose good increments, so ones that work. It wouldn't make sense for me to go up by 2's because I have a lot of space in that independent axis. Okay, so you want to make sure that you choose an appropriate increment. 6, there we go, 7. Okay, now we'll look at total charge. So total charge, this is in dollars. Okay, so we have a lot of space. We'll look, our lowest value is 50 and our highest value is 330. Okay, so it probably would make sense if we went up by 20, 40, 60, 80, 100. We can go every 5 boxes, so one box represents 20. Okay, so that'd be 100, 1, 2, 3, 4, 5, 200, okay, 300, 400. Okay, and basically you are going to write out the coordinates. Okay, so the coordinates that exist, I can highlight here in orange. Okay, so we're going to find 0 and 50 on the grid. So we'll just watch what I do with my pen. I'm going to go 0 on the x-axis. I'm going to go up 20, 40, 50. Okay, so halfway in between 40 and 60. Okay, then I'm going to make my coordinate of 2, 120. Okay, so how we would write that would look like this: 2, 120 with your x comma y coordinate. So I'm going to go and find my 2, okay, and then go up to 120. There we go. All right, let's go to 4, 190. Here we go. 6, 260. Okay. Oh, you know what? There we go. 6, 260, and then 8, 330. 300, 320, right there. Okay. Now, of course, you would take a ruler and you would join those dots, and we would decide based off of this if this was a linear or nonlinear. Okay, so based off of the line I just drew, it's definitely linear, and the reason why it's linear is because it's a straight line. Okay, it doesn't look like a curve. All right. Okay. So that's just great. We'll move on to our next portion. So topics CD, so line of best fit, trends, increasing, and so forth. Okay, so I have actually some notes here. Okay, so the notes say when describing a relationship, you can assess the correlation. So we're going to look and see if our scatter plots are actually positive, negative, or no relationship. We're going to determine its strength. So they're strong or weak. Some teachers also teach moderate, right? So if it's kind of in between. And whether or not the relationship appears to be linear, so makes a straight line, or if it's nonlinear. Nonlinear could be a curve, so basically not a straight line. Okay, so I'll let you read over these correlations. Okay, so these are just some notes that you can follow. And I'm actually going to draw an example of each. Okay, so when you have a strong linear relationship, basically what you would have is a scatter plot that looks like it's increasing to the right, and is increasing in value over time. Okay? If it is a weak linear relationship, okay, so what you'll notice about this is the points are a little bit more dispersed. They're further away from a centered line that could be created, but we still can tell that it's still increasing in this case. All right, no relationship. No relationship looks really random, where we can not tell if it's increasing, decreasing. So it's basically just a bunch of dots that don't really represent anything. And then nonlinear basically looks like we're drawing a curve. Okay, so you can see here, it follows the path that looks like this, so it's not actually a straight line. All right, okay, so I'm going to get you to try these examples. So there's examples 1, 2, and 3 to try. Okay, so I'll just move down and we'll discuss correlation. Okay, so for correlation, will each of the following sets of data show a positive correlation, a negative, or no correlation? And we're going to give a reason for your answer. Okay, so I'm also going to use graphs to represent them in a one-quadrant graph, just so we can draw a visual. So in the number of pages left to be typed in your essay, and the number of pages already typed. Okay, so definitely in the independent axes, this would represent the number of pages typed, and in the dependent would be the number of pages left. Okay, so essentially you would start with, say, 1,000, okay, maybe not 1,000, maybe we'll say 10 pages, to pretend it's a really big essay, and this is going to represent a negative correlation. And the reason why is because you start with your total that you need to be typed and eventually decline the more pages that you do or type out. Okay, the size of a student's hand and the number of rings the student owns. So this one would be no correlation. There's no relationship, right? Somebody can have a very small hand and have no rings, and somebody can have also a very small hand and have many rings. Okay, so you can buy as many rings as you like. You're not limited. The outside summer temperatures and the number of people swimming. So definitely the last couple of days have been super hot. Okay, so if we were to think of our swimmers and temperature, swimmers. So the higher the temperature, the more swimmers. Okay, so this would be a positive correlation. The depth of Lake Ontario and the amount of rainfall and snowfall for that year. Okay, so if there is precipitation that is created, this also would be a positive correlation. So the more rain or snow adds to Lake Ontario, creating it to be a deeper body of water. Okay, last couple here. Even if you want to pause the video and see if you can get them, but I'm just going to write out your solutions so that you can read them on your own and compare independently. And if, of course, you have any questions about them, feel free to send me a message and we can talk about them. But hopefully by now you get the drift. Okay? Okay, line of best fit. I'm going to get you guys to do this as part of your homework support. So just describing the type of correlation, that kind of stuff, and practicing the line of best fit. Okay? Okay, a table of values. I've actually already done this up above in the example that we did right here. Okay, but I'm going to show you how to do it again anyways, and we can discuss how you would do so if you are given values and how to plot that out. Okay, so you're given your x values. To find your y values, we're going to sub in our x value. And remember, every time you do a substitution, you should always include a set of brackets. You know what? I don't have enough room, so I'm not going to include the y because I don't need it. So I'm going to go negative, -2, plus 4. Negative, -1 plus 4. Negative, 0 in brackets, plus 4. Negative, plus 4. -2 plus 4. Okay, so what we should have for these values, so two negatives touching makes a positive, so that would be 2 plus 4, which would be 6. So meaning our coordinate would be at -2, +6. -1 times a negative would be +1. 1 plus 4 would be 5. So that coordinate would be at -1 and 5. So you'll notice all of our x values are just rewritten, and the work that we worked out to figure out what our y value was, we wrote in the y position. Okay, so now we're going to take each coordinate. It's already labeled for you, so really you just need to plot your axes, or plot the point on your axes. Okay, and we'll put arrows at the end just to show that this goes on and on. Okay, it's pretty much the same thing here. If you want to change that half to a 0.5, you can try this on your own and just see if you can graph it. Okay? Okay. First differences. So we'll talk a bit about first differences and what's represented in first differences. Okay, so they're actually one of the key components into identifying if there is a linear relationship, of course in a table of values type of question. Okay, so there are 3 ways in total how to determine if we know it's a line. So the first is looking at the graph. So if it looks like it's a straight line, it's going to be linear. Okay, looking at the table of values, so looking at the first differences, which is what we're going to talk about right now, and then looking at the equation. Okay, so you can see here, this is definitely a linear example. It looks like a line. This for sure is a nonlinear. You'll learn this when you get into grade 10, where we see something that's quadratic. Okay, so what we're going to do here is determine our first differences. Okay, so how we do that, it's important to also acknowledge the x's. Okay, so the x's look like they're increasing by 1 each time. So you can add that on the side because it is important to acknowledge what your x's are increasing by. But it's really important to determine the change in your y. Okay, so as a starter, I like to start at the bottom. Okay, so you can see it's already highlighted for you, and you're basically going this way. So 28 minus 25 is 3. Okay, 25 minus 22 is 3. 22 minus 19 is 3. 19 minus 16 is 3, and this is a good sign. This means that we actually are looking at a linear relation. Okay, so what do you notice about the in the column for the x values? So they all increase by 1. Okay, what do you notice about the first differences? They're, oops, it's not agreeing with me today. They are the same. Okay, so this means if your first differences, I'm going to say FD for short, are constant, and the word constant just means the same. It is linear. Okay, so that's something that you need to look out for. So I have 4 examples here that you can try on your own. You would do the exact same thing. So again, start at the bottom, -5 minus -2. Okay, -2 minus 1. And just see if it is linear or nonlinear. If your first differences are not the same, of course that means it is nonlinear. Okay, direct variation. I'm just going to go over what the idea of direct variation is because tomorrow we're going to be looking at it a little bit more closely. So direct variation is when there is a mathematical relationship between 2 variables that can be expressed by an equation in which one variable is equal to a constant times the other. So for instance, if you have a part-time job or are looking into part-time work, for every hour that you work, you earn a certain rate of money. Okay, in this case, we're looking at some sports car, and we see that there's a mileage of 6 kilometers per liter on the highway. So that means if they drive 0 kilometers, so meaning they don't leave the parking lot, how much distance would be driven? Well, of course, 0. Okay, what if we drive 1 kilometer? Oops. 6 times 1 would be 6. Okay, so basically what you're going to do in this example is put it in a table form and then also create your scatter plot. Okay, perfect. All right, this is the last little section here. Thanks for being patient and going through this document with me. Okay, so the last thing is actually looking at speed. Okay, so speed can be calculated in the formula of delta y over delta t. So that little triangle means delta. Okay, and that is the same as rise over n, which is something we're going to spend some time on our next unit. Okay, so we're going to find the change in y, which is the distance, and divide it by the change in time. So we're actually going to observe 3 parts. We're going to observe what happens from part A. We're going to observe what happens in part B. And we're going to observe what happens in part C. Okay. So the distance traveled. So if we see here in kilometers, it looks like in between that time, 120 kilometers was traveled over the span of 2 hours. Okay, so to get speed, we just have to divide it. So you would do 120 divided by 2, and we would get the speed 60 kilometers per hour. Okay, in part B, you'll notice there's no movement, so it's actually 0 kilometers, but still 2 hours have passed. So then we would just do 0 divided by 2, which is still 0 kilometers per hour. Okay, and then part C. Okay, so for distance traveled, okay, because we're going downwards, we're actually not increasing, right? When we're increasing, that would represent the idea of a car moving forward to a certain direction. So for instance, if you're at home and then you're going to school, that would represent you going to a new location. This little picture could represent you going to school, stopping at Tim's to get some breakfast, and then returning back because you forgot your notebook. Okay, so our distance traveled, because we're going downwards, is actually a negative 30 kilometers. We're not moving towards our destination. Okay, still 2 hours have passed, and then to get the speed, we're going to divide it. So negative 30 divided by 2, which is negative 15 kilometers per hour. Okay. Now to find the total distance traveled, we're going to look at how much distance actually was in the vehicle. Okay, so just here, total distance traveled, it kind of got cut off a bit. So this is just regardless if we're moving forward, backward, just how long were we in a vehicle. Okay, so definitely in part A, we were in the vehicle for 120 kilometers, and also we were in the vehicle for 30 kilometers, just not moving towards our destination. So in total, we had 150 kilometers of travel time. Okay? Okay, so I'm going to end here. Thank you for tuning in to the day 3 notes. If you need any clarifications, please let me know, and I will be happy to get back to you. But again, please go